Bismillahirrahmanirrahim. Let's start our next lecture on heat and mass transfer. Now we are going to start the problems of chapter number 3. Till now we have covered the theory that in the form of the thermal networks in chapter number 3. Now we are going to take some problems on the same to have an in-depth understanding. Starting with 3-3, it says that the rear window of an automobile is defogged. It is defogged by passing warm air over its inner surface. So warm air is being passed over its inner surface, means the inner surface of the rear window of the rear glass, and it is being defogged. So we will get rid of the fog. Now if the warm air is at 40 degrees Celsius, so inside the car the air which is being blown away is at 40 degrees Celsius, and the corresponding convection coefficient between the inner surface of the glass and the inside air is 30. What are the inner and outer surface temperatures of the 4 mm thick window glass? So we have to find out the inner and outer surface temperatures. Temperature at the inner surface of the glass, rear window, and temperature at the outer surface of the glass or rear window. If the outside ambient air is at -10 degrees Celsius and the convection coefficient between the outer surface of the glass and outer air is 65. So let's say we have this glass. You would have seen that in an automobile, in some types of automobiles, you turn the button on and then it starts blowing the air on the surface of the rear window when it gets foggy, and then this is how it is defogged. So this problem is about that particular phenomena. So we have this 4 mm thick glass, and we have to find out the inner and outer surface temperatures. So this is the inside of the car. This is inside of the car. You can see that the temperature is of the hot air inside the car is 40 and convection coefficient is 30 watts per meter square Kelvin. And the temperature outside the car is -10 degrees Celsius and the corresponding convection coefficient has a value of 65. So we can call the temperature at this face, at this surface, as Ti or Tsi, whatever you like to call it. And similarly, the temperature over here may be denoted as T0 or Ts0. It depends upon you. So over here we can see that there are three resistances. One would be the conductive resistance offered by the glass. Through the glass it would be conduction, and since the air is flowing over the inner surface of the glass and over the outer surface of the glass, so there would be a convection resistance on either side of the glass. Wherever there is convection, there would be a convective resistance. Wherever there is conduction, there would be conductive resistance. So therefore our thermal network would be having three resistances. One would be conductive in nature, L over Ka. Since it is conductive in Cartesian coordinates, it would be L over Ka. And as mentioned earlier, the convective and radiative resistances are independent of the coordinate system. So the convective resistance would be 1 over Ha, and it would be 1 over H0A, 1 over Hia and 1 over H0A. You would probably be thinking, where is area? So we will see it in a bit. Now at the nodes of the thermal network, this convective resistance, which is 1 over H0A, so the convection is taking place between the fluid which is at T infinity naught and the outer surface of the glass which is at Ts outside. So at the two nodes we would have T infinity naught and Ts naught. Similarly, the conduction is taking place through the thickness of the glass, and the glass faces are at temperatures of Ts0 and Tsi. In fact, we have to find out Ts0 and Tsi. These are the two unknowns. So between Ts0 and Tsi, between the two nodes, at the two nodes we would have those two temperatures, and between these two nodes we would have conductive resistance offered by the glass material L over Ka. Similarly, between Tsi and T infinity I, there is convection taking place. So at the two nodes we would have temperatures of Tsi and T infinity I, and in between these two nodes the resistance would be convective, 1 over Ha or 1 over Hia, and this would be the direction of heat flow. This would be the direction of heat flow, because it is important that you determine the direction of heat flow. It is very important. The heat will flow from higher temperature to lower temperature, so therefore it will flow from 40 degrees Celsius to minus 10 degrees Celsius. So we have to find out the temperatures at two surfaces, Tsi and Ts0. Now in order to find out this Ti and T0, see, how can you find out Tsi and Ts0? First of all, you can apply the convection expression between this surface Tsi and T infinity I, right? Q is equal to Ha delta T. But again, in order to find out, so it would be Q is equal to Hi multiplied by A multiplied by Tsi minus T infinity I. So we do not know Q and we do not know Tsi, and we do not know area as well. So area is not a problem, because we can always deal in, if we do not know the area, so instead of dealing in Q, we can deal in Q by A, heat flux, right? So knowing area or having no information about area would not be problematic at all. So the thing is that if we want to find out Tsi using Q is equal to Ha delta T, we do not know Q. So therefore we first somehow need to find out Q. So over here we can also find out Q using conduction through the glass. How? Minus Ka times delta T means Tsi minus Ts0 over delta T minus Ka delta T over delta X, where delta X is the thickness is 0.004. See, we are having the same problems. We do not know the temperatures at the two faces, and if we apply convection equation over here, outside of the glass, Q is equal to Ha delta T, where H would be H0. So the thing again is that we do not know Q and we do not know Ts0. So what we would be doing first, we would be finding out somehow or other Q. If we can somehow find out Q, we can then apply the expressions of convection at least to find out the required temperatures. Now the thing is, how do we find out Q? First of all, we cannot find out Q using this convection alone, inside convection alone, or conduction alone, or outside convection alone. So we would not be able to use Q as minus K delta T over delta X or Ha delta T. So one easy way is to find out over here, since we are dealing chapter number 3, thermal networks. So we can always write Q as delta T over resistance. As delta T over resistance. And the delta T that we will use is that delta T which has been provided to us. See, how many temperatures are we given out of these 4? We are only given T infinity naught and T infinity I. So we will write Q in terms of delta T over resistance, and delta T would be T infinity I minus T infinity naught, because these are the only temperatures that are provided. These are the only temperatures that are provided. So we are trying to find out Q with the help of the given data, and the given data is T infinity I and T infinity naught. Now if we write in the numerator the temperature difference as T infinity I minus T infinity naught, then what we will write in the denominator? We will write all the resistances that fall in between T infinity I and T infinity naught. Means we will write 1 over Ha, L over Ka and 1 over H naught A, all three. So we will write Q as T infinity I minus T infinity naught, and in the denominator we will write all the three resistances, because in between those two temperatures, in between T infinity I and T infinity naught, we have got three resistances. As just described, since we are not given the area, so we will take the area common out of the denominator, which will go into the numerator, and it will get multiplied with delta T. And from here we will take the area into the denominator of Q, into the denominator of the left hand side of the equation, and we will call this Q by A as heat flux. So now T infinity I is 40, T infinity I is 40, minus T infinity outside is minus 10, so minus 10, over 1 over Hi. Hi is given to us as 30, plus L over K. Now length is not the length, rather it is the thickness of the glass. Thickness of the glass is given to us as 4 millimeters, so it is 0.004, over thermal conductivity. Thermal conductivity of the glass is not provided. See, if we are not provided the thermal conductivity of any material, that is not a problem unless we know the material itself. So since we know the material, that it is glass, so we can always make use of table A at the end of our book. Over there we are given the values of the thermal conductivities of various metals, non-metals, etc., etc. So if you refer to that table A, I have brought an image of the same. So in table A3 we will find glass, and we are given over here the conductivity of the glass is given at 300 Kelvin. Right, so 300 Kelvin means we are talking about 27 degrees Celsius. So, and it is 1.4 watts per meter Kelvin if we say it is Pyrex glass. If you take a look at that table, you will find that apart from this particular set of value for glass, there are listed a lot of thermal conductivities for various values of thermal conductivities for a lot of materials at different temperatures: 300 Kelvin, 400 Kelvin, 600 Kelvin, 800 Kelvin. But over here we are only given temperature of 300, means 27 degrees Celsius, so we have to live with that. Now 27 degrees Celsius doesn't seem to be a very, see over here the temperature would be somewhere between 40 and minus 10 degrees Celsius, and over here it would also be between 40 and minus 10 degrees Celsius. See, we know that heat is flowing in this direction, so therefore TSI would be greater than TS naught. So we would be close to 27 degrees Celsius, if not very close to 27 degrees Celsius. So this is how we look at the values of thermal conductivities from the table. So K has been taken as 1.4 and H naught is given to us as 65. We are only having the table for the values of thermal conductivity. We do not have a table for the values of H, because H is not a material's property, whereas thermal conductivity is a material's property. So if we work the things out, we will get this heat flux as 968 watts per square meter. Now after knowing this thing, we can find out TSI. How? By applying same thing, which is Q is equal to delta T over resistance across these two nodes. How we will write it? We will write Q as T infinity I minus TSI over 1 over HIA, where A would be taken into the numerator and then into the denominator of Q, and we would be calling it heat flux. Now in here we know the heat flux as 968, T infinity I is given to us as 40, TSI is the only unknown, and HI is given to us as 30. So we will be able to find out the inside temperature of the surface of glass as 7.7 degrees Celsius. We could have found out in another way. See, we could have written this heat flux as Tsi minus T infinity naught. Tsi minus T infinity naught. But then in the denominator, we would have written two resistances. So it's a longer route, but it will give you the same answer, right? Now, in order to find out Ts naught, we can write Q as delta T over resistance, and we can write delta T as Ts naught minus. There are various forms that can be used. For example, we can write what I have written over here is Q heat flux as Tsi minus Ts naught over the resistance that fall in between these two means L over Ka. Now Ts naught is the only unknown because heat flux is 968, Tsi has been calculated as 7.7, the thickness of the glass is 4 millimeters and the conductivity of the glass is 1.4 watts per meter Kelvin. So we would be able to find out the inside, sorry, let's correct it, it's outside. The outside temperature of the glass is 4.9 degrees Celsius. This is one way of finding it out. Q can also be found out using this manner, Ts naught minus T infinity naught over this resistance 1 over H naught A. Or there is another way we can find Ts naught out. How? Write Q as T infinity I minus Ts naught. Then in the denominator we would be writing two resistances. So there are various ways that you can write the heat as delta T over resistance, but that would depend upon the parameters that are known, that have been calculated, that have been provided. Of course, we would not like to have more than one unknowns in a single equation. There is part B to this problem as well, and as far as I remember, it was about the plotting of some temperature graph, but for the time being we would be restricting ourselves to the first part only. This is what we have just covered. Now let's take the next problem, 3-4. It says the rear window of an automobile is defogged. So it is again the similar problem. How it is defogged? By attaching a thin transparent film type heating element to its inner surface. See, over there in the previous problem we were removing the fog by blowing the hot air over the inside surface. Now they are saying that we are getting rid of the fog by attaching a thin transparent film type heating element to the inner surface of the rear window. Probably you would have seen those orange lines on the rear window of certain automobiles. It is that thin transparent film type heating element that is being discussed over here. So what happens, those of you who would have experienced, what happens is that you press a certain button and no hot air blows. Rather you would have experienced, if you would have experienced, that defogging starts around those orangish lines, because those are the heating elements through which the current passes, and as the current passes through it, the heat is dissipated, which removes the fog from the glass. Now by electrically heating this element, a uniform heat flux may be established at the inner surface. This is what I have just explained to you. So over here we have this diagram. We have this window, we have this glass window, rear glass, and now it is the inside. Now this is the inside and this is the outside. So inside we have this thick black thing is the film type heating element. Now for a 4 millimeter thick window glass, it is the same glass that is being discussed over here, which was in the previous one, with the exception that over there fog was being removed by blowing the hot air, whereas over here the fog is being removed by this thin film type heating element. Now for a 4 millimeter thick window glass, determine the electrical power. So where is electrical power coming in? It is coming into the film type heating element. So we have to determine the electrical power required per unit window area. So again we would be dealing in flux and not Q. To maintain an inner surface temperature of 15 degrees Celsius. To maintain an inner surface temperature of 15 degrees Celsius. Inner surface temperature means inner surface temperature of the glass. When the interior air temperature and convection coefficient are 25 degrees Celsius. See, over here the interior air is at 25. Whereas in the previous problem, since defogging was being achieved by passing hot air, so it was at 40 degrees Celsius. But over here, we are not achieving the defogging by hot air, so therefore the inside air is at normal temperature of 25 degrees Celsius. And HI is 10 watts per meter square Kelvin. While the exterior air temperature and convection coefficient are minus 10 degrees Celsius and 65. So outside conditions are the same. However, the inside conditions have varied now. This is a mistake. HI is not 65, rather it is 10. It is 10. So let's start drawing the thermal network. See, we have this glass window. So associated with the glass window, we would have the conductive resistance in Cartesian coordinate system, and that resistance would be L over Ka, where L would be the thickness of the glass, which is again 4 millimeters, and K would be the thermal conductivity of the glass, which would be 1.4 watts per meter Kelvin. And we do not need to get worried about area, because area we would be dealing in Q by area, means heat flux. Now outside the glass there is air, so air is blowing over the outside surface of the glass, which is the case of convection. So associated with this convection process, there would be a convective resistance, means 1 over HA or 1 over H naught A, whatever you like to call it, or 1 over H2A. What is the addition over here in this problem? The addition is that we now have this film type heating element. So wherever there is a material, it would offer some resistance. Large or small, that is another story. Wherever there is material, it would offer some resistance. So now it would depend upon the type of the material. If that material is highly conductive, so it would result in less resistance, and vice versa. So since we have attached a film type heating element to the inner surface, so it will also offer conductive resistance, because it is some material, which would be delta X over Ka or L over Ka, where L or delta X would be the thickness of the film type heating element, over K means conductivity of that heating element. And between that heating element and the inside air, there would be convection, and that convective resistance would be given as 1 over HA or 1 over H1A or 1 over HIA, whatever you like to write. See, what do we know? We know T infinity. Allah. So now we know T infinity inside, means we know this temperature, and we also know this temperature as minus 10. Do we know the resistances? Do we know the outside resistance? We do, because we have the value of H2 and we would be dealing in per unit of area. Do we know this resistance? We do, by the glass, offered by the glass, because we know the thickness of the glass and we know the thermal conductivity of the glass as well. Do we know this resistance? This one. So we know these two resistances. We do, because we have the value of Hi as 10. Now do we know this resistance offered by the material, offered by the film type heating element? Are we given its thickness? No. Are we given its conductivity? No. So we would not be able to find out its resistance. So if we try to find out Q again using this delta T over the sum of those four resistances, we would never be able to find out Q because we do not know this particular resistance offered by the heating material. And we cannot find out its thickness, and we cannot also find out its conductivity because we do not know the material itself. Now, if you take a closer look at the problem again, see, as I have explained in some of the previous classes, that you need to look at some keywords. Now, what is the keyword over here in this problem? The rear window of an automobile is defogged by attaching a thin, transparent, film-type heating element to its inner surface. See, it is the word thin that requires your attention. So you are being told that this L or this delta X of the film type heating element is very small, it is thin. See, when you see the word constant properties, you take conductivity as constant. When you see the word steady state, you take dava T by dava T as constant, etc., etc. So there have been certain words that require your attention. Now over here, the word that requires your attention is the word thin. So if this heating element is thin, it means that L is very small quantity. So if numerator is very small, so what would happen to the resistance? Resistance would be having a very small value. So what this thin word is telling us is to neglect this resistance. What this thin word is telling us is to neglect this resistance because it is so thin that its resistance would be negligibly small. So therefore what will happen now is that our thermal network will be reduced from 4 resistances to 3 resistances. Resistance offered by the glass and convective resistance on both sides, 1 over HIA, 1 over H naught A. And what is this Q? This Q is the Q of heater because it is the heater through which the electrical energy is passing, and it is that point where the heat input is coming from. Now see, T infinity I remains T infinity I. T infinity 2 or T infinity naught remains T infinity naught. See, when we are neglecting this resistance, what will happen is that the two temperatures would become same. When we are neglecting this resistance, then those two temperatures would become same. Otherwise, if there is a finite resistance, then there would always be a drop in temperature. However, if we are saying that the resistance is negligible or it is negligibly small, then those two nodes would become a single node. Those two nodes would become a single node, and those two temperatures would then be the same. So therefore those two temperatures would be TSI, means temperature at the inner surface of the glass, and this node would have temperature of TS naught, the temperature at the outer surface of the glass. Then what? See, where will the heat flow? What is the direction of heat flow? Over here it says it is the direction of heat flow, but you need to make the direction of heat flows yourself. See, heat flows from higher temperature to lower temperature, right? So over here it is 25, this temperature is 25, this temperature TSI is 15, it is 15 degrees Celsius, and then it is minus 10. So heat will flow in this direction, the direction which has been made. So the heat will flow from higher temperature of 25 to lower temperature of 15, and from 15 to lower temperature of minus 10. So this would be the direction of direction of heat flow. But what will happen is that the heat will start flowing from 25 to 15 degrees Celsius. But what is happening at this node at which the temperature is TSI? At this node there is further heat input. There is further heat input. And the heat which is coming in will join the heat which is coming in from the first resistor. Let's say if this is 5 and if this is 10, so 10 will join 5, and then it is 15 which will flow further. So the same 5 will not be flowing through this resistor, through the second resistor or through the third resistor. Why? Because in this 5 we are adding 10. So from this node onwards, from this node which is having a temperature of TSI onwards, so the heat which would be flowing through this second resistor would be 15, and through this third resistor would also be 15. So if we call this Q1, so QH joins Q1, and from this node onwards it would not be Q1 or QH alone, rather it would be the sum of the two, which we may call Q2. So if we call this resistance as R1, this as R2 and this as R3, so Q1 is passing through R1, whereas Q2 or Q total, because Q2 would be the sum of Q1 and QH, Q2 will pass through R2 and Q2 will also pass through R3. So Q2, which we may also call as Q total, will be the sum of Q1 and QH, and it will pass through the second resistor and the third resistor. Kindly note that if Q2 is 15, then 15 watts per square meter will pass through R2 and 15 watts per square meter will pass through R3. 15 will not pass through R2 and R3 combined. Kindly note that very carefully, that Q2 will not pass through R2 and R3 combined. Rather, Q2 will pass through R2, and the same Q2 will also pass through the third resistance, R3, 1 over H naught A. Why? Because the resistances are connected in series, and you may make an analogy with the electrical resistance network. So what we were asked to find out? We were asked to find out this heat input through this electrical heater. So we have written this thing, and then QH can be written as Q2 minus Q1. Q2 minus Q1. And what is Q2? Now Q2 can be written as TSI minus TS naught over L over Ka. But we will not write it in this form. Why? Because we do not know TS naught. Q2 can also be written as TS naught minus T infinity naught over 1 over H naught A. But we will not write Q2 in this form either. Why? Because we do not know this temperature. Again, kindly remember, recall, kindly note that Q will be written in that delta T over resistance that we are given the information about. So we are given the temperature values of TSI and T infinity naught. So therefore we are bound to write Q2 as TSI minus T infinity naught. TSI minus T infinity naught. And then what we will write in the denominator? Both the resistances that fall in between Tsi and T infinity naught, means L over Ka and 1 over H naught A. L over Ka and 1 over H naught A. Minus Q1. Q1 only passes through the first resistance. So Q1 will be written as, again, in the same form of delta T over resistance. Delta T would be T infinity I minus Tsi over resistance is 1 over Hia. 1 over Hia. Again we know Tsi, T infinity naught. We know the thickness of the glass. We know the K of glass as 1.4. We know H naught. We know T infinity I. We know Tsi and we know Hi. What we do not know is the area. So we would be working in terms of per unit areas. We will take area from here into the numerator, and then we will take the area common from both these terms, and then we will bring the area into the denominator of QH by A, and we would be calling it QH double dash, means heat flux, thermal heat flux, heating flux. And we know all the values. Tsi is 15, T infinity outside temperature is minus 10 degrees Celsius. Kindly note that you need to keep the temperatures either in Celsius or Kelvin, but you need to follow one notation. Thickness of the glass is 4 millimeters, K of glass is 1.4, watts per meter Kelvin, H naught is 65, Hi is 10. So we get this QH flux as 1270 watts per square meter. Let's take the next problem, which is 3-7 of the 7th edition of Incorpore and Leave It. It says that the walls of a refrigerator are typically constructed by sandwiching a layer of insulation between sheet metal panels. So the walls of a refrigerator, because what we see over on the outside of the refrigerator is a sheet metal panel or a plastic cover, and we do not see the insulation, but there must be insulation, otherwise the heat will flow from outer hot air to the inner colder environment, and there would be a huge heat loss, and the things that we want to be kept at lower temperatures will get perished. So the walls of a refrigerator are typically constructed by sandwiching a layer of insulation between sheet metal panels. So there would be insulation sandwiched between sheet metal panels, means there would be sheet metal panels on both sides of the insulation. This is how we make a sandwich, right? So there would be an insulation. This is the insulation. This is the insulation I, and surrounded by two sheet metal panels. This is one panel and this is the other panel. Consider a wall. So see what is happening over here. This is the case of a composite wall, isn't it? This is the case of a composite wall where the wall is composed of insulation and sheet metal panels. Now consider a wall made from fiberglass insulation of thickness of thermal conductivity 0.046 watts per meter Kelvin. So this insulation is having a thermal conductivity of 0.046 watts per meter Kelvin and a thickness of 50 millimeters, and steel panels. So the wall is made from insulation and steel panels have thermal conductivity of 60, because steel is a good conductor of heat. But why we are putting the steel panel over here? For the structural stability of the refrigerator, in order to give it some strength. So it has the conductivity of 60 and it has a thickness of 3 millimeters. So if this composite wall composed of the insulation and sheet metal panels on both sides separates refrigerated air which is at 4 degrees Celsius inside the refrigerator from ambient hot air which is at 25 degrees Celsius. See, this is the inside refrigerated air which is at 4 degrees Celsius, and it is the outside ambient air which is at 25 degrees Celsius. So this wall is in fact separating the inside refrigerated space from the outside hot space. So see, there would be a conductive resistance offered by the insulation, which would be L over Ka, and then there would be the conductive resistance offered by the sheet metal panel, which would again be L over Ka, and then we have the panel on the other side of the wall, on the other side of the insulation. So it will also offer conductive resistance in Cartesian coordinates, which would be represented as L over Ka, and then on both sides of the sheet metal panel there would be convection taking place, because inside there would be the refrigerated air, outside it would be the hot air. So therefore wherever there is convection, there would be a convective resistance. So the convective resistance inside the refrigerator would be 1 over HIA, and the convective resistance outside the refrigerator would be 1 over H naught A. The inside temperature is 4 degrees Celsius, outside temperature is 25 degrees Celsius. So what we need to find out, if all those conditions exist, he is asking us to find out the heat gain per unit surface area. Means how much heat is flowing through per unit area of this wall, of this refrigerator wall. So we have to find out Q by area. So that is why all those resistances are written in terms of per unit area, because we would somehow be getting rid of the area. Coefficients associated with natural convection at the inner and outer surfaces may be approximated as 5. So the convection coefficients associated with natural convection, both inside the refrigerator and outside the refrigerator, have a value of 5 watts per meter square Kelvin. So this is the thermal network. So what would be the direction of heat flow from higher temperature of 25 to lower temperature of 4 degrees Celsius? This would be the direction of heat flow. So how would you be able to find out the heat transfer? See, we will be writing Q as delta T over resistance, and what temperatures are we given? We are only given this temperature and this temperature. So we have no choice but to write this temperature difference into the numerator. So what we will then write into the denominator? We will write all the resistances that fall in between those two temperatures. Means all 5 resistances. 1 over H naught, L over K of panel, sheet metal panel, L over K of insulation, L over K of panel again, and 1 over HIA. Right? So we will write all the 5 resistances in the denominator. Again we would be doing the same thing. We would be taking the area common out of those 5 terms. We will take that area into the numerator and then into the denominator of Q, and we would then call this Q by A as the heat flux. So H naught is given to us as 5. See, there would be 2 same resistances offered by sheet metal panel. Why? Because they have got the same conductivities and same thicknesses. So we can write it as one term, 0.003 3 millimeters is the thickness of the sheet metal panel, and 60 is the conductivity of the steel panel, and then we can multiply it by 2, because this term and this term would exactly be the same, because they have the same thicknesses and conductivities. And then L over K of insulation, thickness of insulation is 5 millimeters or 50 millimeters, whatever is provided, and K is 0.046 watts per meter Kelvin, and HI is 5. So the heat flux that is flowing from one end to the other is 14.1 watts per square meter.